Okay, today's lesson is on 5.2 mean value theorem. This lesson should really be renamed to mean value theorem and the first derivative test. So we're actually going to discuss the first derivative test in the notes, and then we're going to talk about the mean value theorem. But since it's already here in the first place, let's go ahead and kind of take a minute to discuss it. So of course, I'm missing some parentheses here, and this is the closed interval AB. There you go. So mean value theorem is where your first derivative is equal to your average rate of change. So your first derivative is here is equal to y2 minus y1 over x2 minus x1, right? So what does this mean? It's asking you when does your derivative, at what x value does your derivative equal to your average rate of change? And in other words, an easier example to understand would be, for example, if I were to take a road trip to LA, which roughly is 360 miles, and the trip took 6 hours. So your average speed would be 360 miles total distance over total time, 360 miles over 6, which is an average rate of 60 miles per hour. Now on this trip, you are not going 60 miles per hour the entire time, but how many times would you at least be reaching 60 miles per hour? At least once or twice or maybe multiple times, right? So I'm asking you, when does that happen? When does your instantaneous speed match your average speed? Right, so that's really what it's looking at for this mean value theorem. There's two mean value theorems. They're short. You shorten it to MVT, right? So the first one here is for derivatives, and then in the later chapters, there's another mean value theorem for a different idea. Okay, all right, and then take some time to read through this. Of course, this is talking about your maximum minimums and when your function increases and decreases and all that fun stuff, right? So of course I'm missing some parentheses here. I'm just trying to show you where they all should be. If I were to make sure I get it here, okay? And then I have something here. So these are for your reading pleasure. I'm not going to go over these because it's more important to really see them in action. Okay, so in 5.1, we started with the graph, and we used the first derivative to find our extrema, our max and minimums, and we gave you a graph to kind of look at, oh, well, after you use analytic methods to find these values, what are they? Are they truly maximums? Are they truly minimums? The graph was really helpful. Now we still have the graph to kind of help us, but we're going to use our graph and our algebra to find these exact values, and we need to find which the intervals on which the function is increasing or decreasing. So reminding yourself that an increasing graph has a positive slope because it's going up, and a decreasing graph has a negative slope because it's going down. Okay, all right, so what we're going to do here is it says use analytic methods to find the local extrema. So we're going to use y prime to help us. All right, so y prime equals 4x cubed minus 20x, and 9 is a constant, it goes away. Remember, we set equal to 0 because that's how we find our extrema. So 4x, factor out 4x, you get x squared minus 5 as your factor. You solve for them, you get x equals 0 and x equals plus or minus root 5. And then the next step that is new now is you're going to do a first derivative test. So what you do is you take these numbers that you just got, you make a number line with it, a very rough number line, just to make sure you can place the numbers. So negative root 5, 0, root 5, right? And then you want to go ahead now to test, right? So this is the first derivative test. You are asking yourself, in this interval, is my first derivative, is my derivative positive or negative? So you pick any number in that interval. Now, since that interval is from negative infinity all the way up to negative 5, you have negative root 5, you have a lot of options. I typically choose the smallest number to work with. So the smallest number I can work with would be negative 3, right? And I usually put it into the one that's already factored out. Because again, all I really care about is the positive or negative value of this result. I don't care about the actual numerical value. So when you plug it into this factored form, you get 4 times negative 3 is negative, and then negative 3 squared is positive. Negative 3 squared is 9. 9 minus 5 is positive. So you get a negative times a positive, you get a final result of negative, which means in this interval, my graph is going down, which yes, you can see from the graph, yes, it's going down first, right? Okay, now pick another number in this interval right here, right? In this interval right here, let me not use arrows, sorry. In this interval between negative root 5 to 0, what would I pick? Well, between negative root 5 to 0, I will pick negative 1. Okay, so same thing, I plug it into 4x times x squared minus 5. 4x will give me a negative number. X squared minus 5 will be 1 minus 5 will give me another negative number, which will get positive. So it's increasing now. Okay, the next interval, I probably pick 1. So 4 times 1 is positive. 1 minus 5 is negative. I get negatives coming down again. And then last but not least, something that's past root 5, I will probably pick 3. So then you get 12, which is positive, times 3 minus 5 is positive. I get a positive, so it's going up again. So notice how my number line here is really mimicking the behavior of this graph. It's decreasing, increasing, decreasing, increasing. One thing to note is that you cannot always expect your function to have these opposite behaviors. So it goes from negative, positive, it goes back and forth. It doesn't always work like that, especially in a graph that we see in the next picture there. Okay. All right. So this gives me a lot, and it tells me that when my graph is decreasing and increasing, it creates a minimum. And then when my graph is going from increasing to decreasing, it creates a maximum. So here in my picture, I have created 2 minimums and 1 maximum. So I do need to know their values. So what I'm going to do now is find the y value. So f values. And I plug in f of negative root 5, f of 0, f of root 5. Again, I'm plugging these into the original function, f up, right? So you plug into the original function, negative root 5 to the 4th power would be 25, minus 10 times 5 is 50, plus 9, that would give me negative 16. And since it's symmetrical, root 5 will also give me negative 16, and plug in 0 will give me positive 9. Okay, now I have enough information to answer all the questions, right? We're looking for when the intervals of increasing, decreasing, and local extrema. So part A says local extrema. So I have a max of 9 at x equals 0. I have 2 minimums, but since they're both the same minimum value, you can write it in one line here. Minimum of negative 16 at x equals plus or minus root 5. My increasing interval is from negative root 5 to 0. And then from root 5 to infinity. And then my decreasing interval is negative infinity to negative root 5. And 0 to root 5. You don't have to put the union sign between these two intervals. We know that it is the combination of these two intervals, or at least the 2 intervals that are both decreasing and the 2 intervals that are both increasing. Okay? All right. Next, we have this function that is missing some parentheses. So this is g of x equals x of 1/3 times x plus 8. So in a function like this, I would not suggest using product rule. I would suggest you multiply this whole thing out and then use simply power rule to go ahead and find the derivative. So multiply this out like first. So x to the 4/3 plus 8x of 1/3. Okay, now I take the first derivative. So g prime of x equals 4/3 x to negative 1/3 plus 8 over 3 x to negative, oh sorry, not negative, sorry, my mistake, positive 1/3, and this is negative 2/3. All right, remember we're trying to solve for these, so you want to rewrite it as one single fraction so that you can go ahead and solve. All right, so you get 4 x to 1/3 over 3 plus 8 over 3 x to 2/3. Now, notice that you have some common denominators, so you simply need to multiply the other side by what's missing, which is x to 2/3, like so. Right. Usually when you do this, this will create a really nice whole x on the top. So 4x to 1/3 times x to 2/3 is 4x plus 8 all over 3 x to the 2/3. And you set equal to 0. And again, the beauty in this is now you can split them up. You can go ahead and split the numerator and the denominator. And you solve, you get x equals negative 2, x equals 0. Now keep in mind you got the second answer from the denominator. So since this is a denominator answer, and this denominator did not occur in the original function here, therefore this is where my derivative is undefined. When is my derivative undefined? Or my derivative is doesn't exist. My derivative does not exist at a vertical tangent or a cusp. All right, and so we'll discuss how we know this is either a vertical tangent or a cusp. If it is a vertical tangent, it goes something like this, where it is increasing to increasing, so there's a vertical tangent right there, or vice versa, it's decreasing, decreasing, vertical tangent here. If it is a cusp, it is going to go increasing, decreasing, here's a cusp, or decreasing, increasing, there's a cusp. So a cusp has sign change, and vertical tangent no sign change. So we're going to see which one it is. Okay, and yes, I know you can look at the graph there, but let's see how analytically this is going to prove what we know. Okay. All right. So we're going to make a number line. We're still going to use the numbers we got from our denominator, even though we know those are where my derivative is undefined, but we're still going to use those numbers. Okay. All right. So now I'm going to do my first derivative test, f prime test. I'm going to test -3, -1, and 1. These are my good numbers, right? So again, I'm going to plug it into this factored form because now it's a lot easier to deal with in this format. And there's a trick here. There's a shortcut. If you take a look at our denominator, you're going to square whatever value it is and cube root it. So no matter what type of value you put in, it's going to be positive in my denominator. So I'm going to make a fraction and show the fact that my denominator is always going to be positive. So that saves my work. I deal with the top. 4 times -3 plus 8, that's negative. That is the final answer of negative, so it's decreasing. -1 times 4 plus 8, that's positive, so this is going to be positive, so it's increasing. And then 4 times 1 plus 8, that's still positive, so it's going to be increasing. So notice now my signs are not alternating, so that's why I warned you from the previous problem. And this one shows me something. It shows me that this is a minimum because it went from decreasing to increasing. And then this value, the 0, remember we said it was either vertical tangent or a cusp. And since there's no sign change here, this is a vertical tangent. Okay. So again, the number line actually tells us a lot of information, more than what you would think it would do for us. Okay. All right. And then last but not least, I do want a y value since I only have a minimum. I just need to find that. So f values, I have f of -2. Which is -2 to the 1/3 times -2 plus 8, which gives me 6 here. But I'm going to pull a negative out of the 2 to the 1/3 because cube root of negative, you can pull the negative outside. So -6 cube root of 2 will be my y value. And now I can answer my question. So part A, B, C. So A says what if my local extreme values, so I have a minimum. So a minimum of -6 cube root of 2 at x equals -2. We don't need to talk about the vertical tangent. It will appear when we talk about our intervals. So what are my intervals of increasing? Well, it went -2 to 0 and then 0 to infinity. You have to pause at the 0 because there's a vertical tangent there and f prime actually doesn't exist there. All right. And it's decreasing from -infinity to -2. Okay. All right, next equation here is a quotient. So you have to use quotient rule on this, all right? And yes, you can see the graph is decreasing the whole way, but this is gonna show us a very good example of how the vertical tangent comes up. Okay, so we're gonna take the derivative. So k prime is low d high minus high d low over low squared. Clean up the top. You never need to clean up the bottom. You will get -4 minus x squared over x squared minus 4 squared. And now you can set equal to 0 to solve. Split them up. 0 equals -4 minus x squared. 0 equals x squared minus 4 squared. This actually gives me 4 equals -x squared, or actually let's make it a little bit easier to see. This gives me x squared equals -4, which is not possible. Since this is an expression I got from the numerator, that means then since I wasn't able to figure out an answer, there's no extrema in this problem. And you can see that in the picture there, right? All right, for the bottom, I go ahead and solve this. I get 0 equals x squared minus 4, x equals plus or minus 2. This was an answer I got from the denominator, and it is the same denominator as it is in the original problem. Therefore, this must be a vertical asymptote. And yes, you already knew that from previous classes, but this is our derivative actually confirming that. And you need to now still use those two numbers to make your number line. Even though you weren't able to get any true extrema, you still need to use those numbers to get to set up your number line to see the increasing decreasing interval. So k prime of -3, k prime of 0, k prime of 3. These are my tests, right? These are my k prime tests. This way, okay, k prime test. Okay. All right, so now what am I getting? I am plugging it into this right here, and there's a lot of shortcuts here. There's a fraction here. What you notice is that in your denominator, you are whatever it is, and it is squared. So no matter what the operation is inside, you're squaring your final answer. So my denominator is always going to be positive. That's awesome. Okay. Same thing with my numerator. Whatever value I plug in is going to be x squared, but then you have a negative in front of it and you have a minus 4. So you are always negative on top. So this is always going to be decreasing. So it's decreasing, 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 which again is supported by my picture here. So this answer is very straightforward. You're looking for whether or not you have an extrema. Do you have any local extreme values? Nope, none. Any intervals on which this is increasing? Nope, none. Intervals on which this is decreasing? The whole thing, but you got to break it up. So it decreases from negative infinity to negative 2, negative 2 to 2, and then 2 to infinity. Okay? All right, so let's double check that we answer all the questions. Very good. Okay. Now I am going to go ahead and figure this one out. This is applying the mean value theorem. So it says, show that the function satisfies the hypotheses of the mean value theorem on the given interval a to b. So in order for it to satisfy the hypotheses of the mean value theorem, it says that the function must be continuous and differentiable. So when is the function continuous? Well, it's continuous if it doesn't have any asymptotes, or it's not a even root function, because even root function is only continuous on one side. It's a one-sided function. Or it is not a natural log function, same thing, it's one-sided, right? So since we have a polynomial function, it is continuous for sure. Is it differentiable? We only have a couple of cases where it's not differentiable. If it has a cusp, corner, or a vertical tangent. Again, this polynomial function does not have any of those, so it is differentiable and continuous. So all you have to say for part 1 is just saying, yes, f is differentiable and continuous on this interval 0, 1. So therefore, yes, it satisfies the hypotheses of the mean value theorem. In most cases of our theorems in calculus, the functions will have to be differentiable and continuous for us to apply any of the theorems that we are going to teach you and then that you are going to use. So it is a very safe bet to say that most of the time they should be differentiable and continuous. Okay. All right, now it says find the value of c on which it satisfies this this formula, right? So there's two parts of the question. You are looking for the derivative, and then you're looking for the average rate of change, and then you set it equal to each other. So this problem is not very straight, like one track down. It is actually two separate problems, and then you set them equal to each other. So you got to make sure you do the two separate parts. I'm going to find the average rate of change first by finding the y values to these x values. So I'm going to find f of 1 and f of 0. F of 1 is 1 plus 2 minus 1. That gives me 2. F of 0 is negative 1. So my average rate of change is y2 minus y1 over x2 minus x1. This gives me 3. Okay. Now, part 2 to my equation is now finding the derivative. So f prime of x is 2x plus 2. And so I go ahead and take that 2x plus 2, that's my derivative, and set it equal to the average rate of change that I just got. And now I solve. I get 2x equals 1, x equals 1/2. So the value 1/2 is in this interval of 0 to 1. So at this value of 1/2, this is where my derivative is equal to my average rate of change. All right. So go ahead and make sure you write this as c equals 1/2, because c is the variable that they use in the formula. So if you don't change it, it's really not a big deal. It's just really looking for a variable. The value at which this average is equal to the instantaneous. Okay. Okay, so now we're kind of taking a break from both theorems, and this is kind of a preview of the next chapter. So we're asking you, what functions have this derivative? What function gives you the derivative of sine x? So you know that the derivative of cosine is negative sine. So in order to get the positive sine x, then your original function must be negative. So your original function is going to be negative cosine of x. But don't forget, you can add any number to this and still have the same derivative, because any constant being added to this function will equal 0. So cu is a constant, okay? Same thing, you have f prime equals 1 over x minus 1. So remind yourself, whose derivative was it to be 1 over x? Well, natural log of x will give you the derivative of 1 over x. So in that same idea, your original function is natural log of x minus 1. And don't forget, you can add a constant to it. And notice that I put absolute value around it because a natural log can only take arguments that are greater than 0. So you put the absolute value of it, you really try to force it to be positive. But yes, we also have this little catch here. So you really don't need the absolute value in this case, but it's not a bad habit to form to really put absolute value around natural log functions to really avoid problem happening. Okay. All right, last one here says, on the moon, the acceleration due to gravity is 1.6 meters per second squared. So I'm just reminding you there's a really good formula that you really should know at this point, that your position function is acceleration over 2t squared plus your initial velocity t plus your original initial position. Right? So that is the formula you should know if you don't want to work backwards. If you know your derivatives well enough, then you can actually work backwards to get this answer if you want. So it says if a rock is dropped into a crevasse, so just a hole in the wall, a hole in the ground, how fast will it be going just before it hits bottom 30 seconds later? So let's find our S of t. So this is part A. So S of t is equal to acceleration is 1.6 over 2 t squared. Our initial velocity, because it's being dropped into the crevasse, our initial velocity is 0. And then because it's being dropped in, our initial distance is also 0, right? And it's gravity, so negative 1.6. So my equation is going to be negative 0.8 t squared. So how fast will it be going? Let's look at velocity. So velocity function will be the derivative of that, which is negative 1.6 t, right? And it says when it hits the bottom 30 seconds later, so v of 30 equals negative 1.6 times 30. That would give me 48. Let's go ahead and look at my units, meters per second. Negative 48 meters per second if we're looking for velocity. If we're looking for speed, it would be just be 48 meters per second, right? Okay. All right. Then it says how far below the crevasse is how far below the point of release hits the bottom of the crevasse. So I know that at 30 seconds it hits the bottom of the crevasse, right? So that means if I plug in 30 into my position function, I will know that 30 seconds later, how deep is it down? That is how deep the whole bottom is. Right, so then you plug it into S of t. So S of 30 equals negative 0.8 times 30 squared. So negative 0.8 times 900. Your crevasse is 720 meters below ground level. Okay. All right. So C changes up just a little bit. It says instead of being released from the rest, the rock is being thrown into crevasse from the same point with a downward velocity of 4 meters per second. So what is happening now, your S of t is equal to negative 0.8 t squared, and then you need to add an initial velocity of downward, so minus 4t, right? And then, but you still start at 0 because you still drop it off from what does it say? It's being dropped into that crevasse, right? So it's starting at 0. So this is your position function. It says, when will it hit bottom? How fast will it be going? So you know that the bottom is negative 720. So negative 720 set equal to negative 0.8 t squared minus 4t. Bring it all over to the left side. Negative 0.8 t squared plus 4t minus 720 equals 0, right? You want to try to solve for the t. And this is not factorable, so you have to use your quadratic formula. So t equals negative b plus or minus b squared minus 4.8 times negative 720 all over 1.6. So then you can actually ignore the negative answer because you don't need negative time. So we get, hold on a second, negative 4 plus root, I really don't want to work all this out, so plus 4 times 0.8 times 720, close my parentheses, divide by 1.6, and my time is roughly 27.604 seconds, right? And then how fast will it be going when it does? So your velocity function is negative 1.6t minus 4. So plug it in, plug 27.604 into your function, which is negative 1.6 times 27.604 minus 4. So negative 1.6 times 27.604 minus 4. I get the velocity to be about negative 48.166 meters per second when it hits the floor with this new change. Okay? All right, guys, that's it for this lesson.